Welcome Engineering Statics. This is ENGR ampersand 214 at Bellingham Technical College. This is the second lecture in our series on equilibrium analysis. In the previous lecture, we basically defined the role of the free body diagram, the equations of equilibrium, the sum of the moments in all three orthogonal directions, and the sum of the forces in all three orthogonal directions have to be zero for something to stay in static equilibrium, which is the condition that we are accepting here in engineering statics. That would be equal to ma if we were in dynamics and allowing acceleration, which we want. So that simplifies our equations, makes them easier to solve. We went over the concept of a rigid body, and that it was necessary for force transmission and for displacement to be the same everywhere in a body, but was not necessary to do equilibrium analysis. We can apply the conditions of equilibrium to something that's rigid or squishy. And most importantly, we went over the different reaction forces and defined different ways that our supports can exert forces and moments in response to applied forces and moments on a body. And we went through a couple of simple examples. So in this lecture, we're going to step through a fairly complicated example and apply all those same techniques to something that really does have a bit of a real-life application. So in this scenario, we've got a signpost. So this is, any roadway sign. This would be any kind of single support column structure that has something hanging off of it that is subject to wind load. So we've got the ground down here with our dotted line sort of representing the soil. We're going to define the origin of a coordinate system there, and we've applied a coordinate system that says our I hat or x-axis is pointing out of the paper, our j hat or y-axis is pointing to the right side of the paper, and our z or k hat axis is pointing upwards towards the top of the paper. So if something is falling down or would have weight, gravitational force exerted on it, it will be in the negative z or negative k hat direction, just kind of for reference. Okay, so we've got a pole, maybe a big metal pole, and it's buried in the ground and maybe in a little bit of a concrete foundation. And what we're needing to know is what are the forces and moments here at the base of the pole. And in a real-life example, this would be used for foundation design. So presumably maybe you're a transportation engineer, you're a structural engineer, and you want to put up a sign somewhere, and you would be communicating these moments and forces with maybe your geotechnical comrade or whoever is designing the foundation to make sure that the sign doesn't twist in the wind, it doesn't sag, it doesn't slump into the ground, doesn't fall over. So we're given a little bit of information. We're told that the sign is subjected to wind load, and we know wind load is going to be a surface-based distributed load, but lucky for us, somebody has given us a force resultant for that wind load, so we don't have to do an integral to figure it out. So somebody has told us what that wind load resultant is, and it's in here, sign subjected to wind load, uniform density 200 pounds. Okay, we'll get to it further on. It may be defined later on in the problem, but we know where it acts. So it doesn't necessarily act right here at the center of mass of the signpost. Notice the sign is 4 feet, kind of in width, and so the center of mass of the sign would be at 2 feet. The wind load is acting at 2.5, which kind of makes sense because it's a little further out where the sign is not shielded by the column from the wind. So we've got an F wind acting at this point, halfway down the sign and 2.5 feet over. The sign itself, the little flag part of it here, weighs. The sign is uniform density with a weight of 200 pounds. So that means we can assign a gravitational weight, a downward force at the center of mass of the sign. So that'll have to be at 2 feet over from one side and 1 foot down in the center and in the negative k hat direction. The post itself is probably metal or a dense wood, and it's uniform density, so we know we can apply that weight gravitational force at the center of mass, which is halfway up it. and it's 500 pounds. And we've got dimensions on our schematic: 10 feet high, 4 feet across on the sign. We have dimensions of the sign, position of the resultant wind load, and we're told that the sign and the post thickness can be neglected. So we don't have to worry about being, how far off we are from dead center on the post. We can assume that the post radius is negligible and the thickness of this sign is negligible. So all we have to deal with are the given dimensions. So that's really going to make our job easier. So someone wants the forces and moments acting at point O, because that's what your foundation designer is going to need. Okay, so we have a lot of choices in terms of how we're going to approach this. And our first idea is how many FBDs, or free body diagrams, do we want? So we can isolate the whole thing and do an FBD of the post and sign combo, and in which case we would only be looking at basically the wind load hitting and the total weight of the body. We'd get a combination weight, or two weights, and apply them in two places, and then we'd have the reactions down here. This total FBD would not consider the force of the post on the sign or the sign on the post. We would eliminate that in that FBD. So another approach would be to say, okay, I'm going to do a separate FBD of just the sign. So that would end up including wind load, the weight of the sign itself, and then any forces and moments that the post applied to the sign. So that now the post is effectively acting as a support, and it can apply forces and moments on the sign, and we'd have to represent those as unknowns and solve them by difference. That's okay. That's very valuable for getting us somewhere. And last but not least, we can isolate the post, and we would end up representing the forces of the sign on the post as some unknown force, and there are definitely going to be some moments applied to the post by the sign, and we'll represent the reaction forces of the ground too. So we have three options for an FBD, and I will admit I started with the post, but I think it's better to start looking at the sign, because that gives us a better idea of what is an applied force and what is a reaction force. Okay, so here's an FBD of the sign. And again, I've got the coordinate axes replicated here so we can remember what direction we're going. And we got a lot of dimensions on this one, so I thought that was a good way to break it out. So let's just step through this. This is the sign, so it's just our little rectangle. We got its 200-pound weight acting here at its center of mass, so that's 2 feet over and 1 foot down, acting here. So if you want to think about this edge already, the fact that we have a load acting at a radius from where the sign is connected to the post means not only is the post going to have to give us some upward force to react with here, it's also going to have to counteract a moment, which is going to try to rotate this sign in the clockwise direction around an axis that's pointing out here, around the J axis. So that's what this force is going to do. It's going to rotate the sign around that axis. So how do we depict that effectively with our reaction force? Well, here's a moment that we're saying that the post is going to have to exert in the J hat direction, and that's going to counteract that turning that the sign's own weight is exerting. In fact, you're going to find out there's a lot of moments. So S represents the force of the post on the sign, and MS is the moment exerted on the sign by the post. And so we've already identified a couple of reaction forces just necessary to account for the sign's weight. Okay, now we include the wind load, and so we've put it appropriately where we're told it goes, and so it's going to basically push the whole sign backwards in the J direction. So this whole thing's going to go backwards. So we're going to need to oppose that. The post is going to need to oppose that with an S sub Y going back the other way. More importantly, we're going to need to counteract a twist. So this wind load is going to want to make the post twist around the z-axis, like so. Twist it straight around. So we're going to need to, the post is going to need to apply a moment to prevent twisting around the z-axis. Now the one that I always find a little bit less obvious is the fact that we are also getting some rotation due to that wind load around the I-hat axis, the wind and the weight. So the sign is actually going to have to apply another force, or excuse me, another moment, not a force, but it's going to have to apply another moment in this direction. And if you want to think about it, it's because we're looking at again here is twisting, so we have to do some envisioning. So wind and weight are going to end up causing a twisting around this axis as well, and that's the one that's a little bit harder to envision. So you have to just kind of think about which way the sign is going to try to rotate due to the applied loads. And so as it turns out, the post is going to have to apply a moment, not a force, but a moment in the x direction. Okay. Or at least we're pretty sure it does. And if it doesn't, we'll solve for equations of equilibrium and find that to be 0. Okay. So to recap, so this is our FBD. Basically, we've had to assume that the post is going to have to exert a force in two directions, z and y, and it's going to have to apply a moment in the y, the x, and the z. So a fairly constrained support is coming from the post. So, and again, this one tends to be the least intuitive, but some people just see it right off, and we know it's there. Okay, so just to recap, S sub y and S sub z are forces exerted by the pole on the sign. So if we want to do an FBD on the pole, these same forces, same magnitude, opposite direction, we would slap straight onto our FBD. And notice we've arbitrarily decided to draw them in the positive direction in this case. So we'd need to draw them in the negative direction on our pole FBD if we chose to do that next. So this is where signs and directions become really important. So don't make sign errors as you're applying Newton's third law, which is what you're doing here. Okay. And the same thing goes with the moments. Okay. So there we go. There's our FBD. And let's go back. If we were to do the post only, and before we do that, let's count up what we know and what we don't know. Because in order to solve for this, eventually we're going to have the same number of unknowns as equations and solve for all of them. So let's just check out how many equations of equilibrium could we write coming out of this FBD. We've got some of the forces in the x equals 0, that's 1. Some of the forces in the y equals 0, that's 2. Some of the forces in the z equals 0, that's 3. We've got some of the moments in the x is 0, 4. Some of the moments in the y is 5. And some of the moments in the z is 6. So we get 6 equations here. And we have 1, 2, 3, 4, 5 unknowns. Pretty good. So we'll be able to solve for something, and then another one will effectively take on a range of values. Eventually we're going to want to get the exact same number of equations as unknowns. So it could be that one of these is redundant. Okay. So let's take a look at what would happen if we kind of did the opposite. So here's an FBD of, I'm going to bump up our magnification a little bit here, our view, so we can see this a little better. So here's an FBD of just the post. I'm going to start with the ground. The ground is a universal connection. It's like a weld. So it can apply a force upward in the J direction and in the X direction. So G is ground force. It can apply a moment in all three directions. So basically it's a complete constraint if it's built right. If it works, it should be applying this. So right there's 6 unknowns. And really this is what we're solving for. So one of the nice things about this FBD is it actually includes the variables that we need to solve for. So this is a useful FBD for us. So let's take a look at what we know and what was coming from the sign. As it turns out, the only force on the pole that we know explicitly is its own weight. So we have all of our unknowns down here coming from the ground, 6 of them. We've got weight, and then all the other forces are coming from the sign. And notice they're going the other way. So we had the forces of the pole on the sign going in the positive direction. Now they're going in the negative because of Newton's third law. And same goes for the moments. They're reactions. So we have 3 of them. So they should all be going in the opposite direction that they did on the FBD of the sign. If they're not drawn that way, that's an error. Okay. So again, we'll get 6 equations of equilibrium. We've got 6, 7, 8, 9, 10, 11 unknowns. So we could get some relationships out of this, but we couldn't really solve for anything, unfortunately. But we could have a good start on things. Okay, so we're basically collecting FBDs and looking at how many equations we'd have to solve, scoping the math. If we did the sign and the post all as one thing, and I've taken out this line here and just tried to represent this as one big body. We have no S's here. We've just got the wind load, the weight of the sign, the weight of the post, and the reaction forces. So here's our ground forces. So this really actually looks like the best candidate to start with, honestly, because we've got 1, 2, 3, 4, 5, 6 unknowns. We've got a 3D situation. We know we have 6 equations. So if we were looking for the ground forces, which is what we were asked for, this single FBD should give it to us. We won't know anything about what's happening between the sign and the post. So, if we had to select a fastener or look at maybe the strength of the material in the pole in the radial direction, not wanting the pole to split as this and have the sag, we'd have to go back up to our other 2 FBDs. But if all we need to know is how to design the foundation, this one will give it to us. We know that right off because we have 6 equations and 6 unknowns. Not that we necessarily want to have to solve that many, but it's very easy to do with matrix algebra, even if we didn't really want to do it by hand. So this was really the most direct path to what we wanted. So that's why we went through those. And actually, if you really want to step through the math, it turns out that it wasn't quite as hard, and so I won't step through every one of these mathematical discussions, but it turns out you really can solve it fairly easily here. So, thought-provoking question: what happens if F winds switch to the opposite direction? Basically, you're going to have a lot of signs switching. The reaction forces are just going to switch directions in that case. Okay, that is it for this lecture. So we will continue a few more lectures with equilibrium analysis, mainly just going through more and more examples of the same type. There's really a set procedure for doing this. Works every time if you're willing to step through it and be very, very careful. So we'll see some of those next.